Okay, so before I start, I think I talked to at least I have sections 8 to 9 and 9 to 10, but the 8 a.m. section said they couldn't find the Zoom recordings for this discussion. Is that true? So
I myself can't find the Zoom discussions.
okay. In that case, what I'm thinking of doing is I will upload the recordings to, say, what do you call it? A YouTube channel. Is that good for everyone? And you could just watch it there.
Yeah, that sounds fine.
Okay. Yeah, I will send the YouTube link later. I'll make an announcement on campus. So, okay. Let's get started. So if you recall, right, the idea of antiderivatives is that derivatives is that it helps you, it's related to like area, right? So, we always take stuff one step at a time, right? So if I wanted the area of something curvy like this, right, you wouldn't like try to do it like directly, right? You would try to, approximate it first and then get a better and better approximation and then see what you could do from there, right? So the idea is approximate area under F, right? Area under F by area of stuff we know, yeah? And we don't know much, right? I mean, from geometry, you probably know like what area of a trapezoid, square, I mean, not square, like square is too easy. Rectangle, right? Triangle, circles, right? So the book chooses rectangles, yeah. So the book chooses rectangles. You can use triangles, trapezoids if you want. It's just rectangles are the easiest, right? So what we're going to do is we are going to first approximate a function by like rectangles, and then we'll see how to improve it, and then we'll get the actual area. Yeah. So let's just go straight to an example. Yeah. If I do f of x is x squared, the idea is I want to use rectangles of the same width. And let's say for the purposes of this example, I want it's from the interval 0 to 3, and I want 3 rectangles. Yeah. That should make things easy, right? Because if you have 0 to 3 and you wanted 3 rectangles, you just go, this is your first one, right? 0 to 1 is your first one, 1 to 2 is your second, and then 2 to 3 is your third. Okay. And it's clear by same width, they are the same width, right? These are all length width 1, if you like, right? The intervals are all width 1. So from here, let's go over the right approximation. So it's exactly as the name suggests, right? Right approximation of 3 rectangles. So you would look at the first interval, right? And you just follow the name. The name says use the right. So we use the right endpoint for the height, right? Because again, rectangles, you need width times, some people call length. I'll just call it height. Yeah. So what height do we take? We take the height at 1. We take f of 1, right? That's what it means for the right. We take the right endpoint. So we take 1. So we take the height at 1, and then we make a rectangle. And then we look at the next interval. we take the rightmost endpoint. So we take the height at 2. And then we have a rectangle. And then lastly, we look at the third interval. And then we take the height at 3. Yeah. And from here, the answer is just area of the sum of the area of the rectangles, right? This first rectangle has width 1 and height 1 squared, right? Because it's f of 1. So this one, and the second one has width 1. Again, they're all the same width. And then 2 squared, right? And then the third one has width 1, and then the height is 3 squared. So it's 1 times 1 squared plus 1 times 2 squared, which is 9 plus 5, 14. Yeah. Everyone follow? So for this example, is this a over approximation of the area under the curve or under? Yeah, over, right? There's like you're overestimating. These are like the overestimates, right? The thing in green. Okay, so let's practice left approximation. So I'm gonna go a little faster. So 0, 1, 2, 3. So left is the exact same thing, the exact same process, right? Look at the first interval, and then you take the height at 0. In this case, the height at 0 is just 0. Yeah. So this is like a rectangle with like no height, because f of his 0 squared is 0. And then you look at the second one, and then you take the height at 1. Yeah. And then you look at the third one, not drawn to scale, by the way. and then you take the height at 2, right? So this thing is the width is always 1. The first one, the height is 0 squared, right? Plus 1 times 1 squared plus 1 times 2 squared. So this is 5, yeah? And is this an under approximation or over? Under, yeah? Here you're just missing the entire triangle. This thing you're missing and this thing you're missing. Yeah. So in general, right, you can start to see for increasing functions, left is like under, right is over. Yeah. And then you can see if your function is decreasing, it's sort of the opposite, right? Left is over, right is under. But I will let you try that by yourself. So let's go over midpoint, the last one. So for now, I'm just going over, how you would just do the approximations. Okay. Midpoint is exact same, right? It's exactly what it sounds like. So in this case, it's easy to know what the midpoint is, right? But maybe for your homework, the number's not as nice, right? Because it's obvious the midpoint from 0 to 1 is 1/2, right? So if I had an interval like A to B, so let's say 7, 15, yeah? How would I find the number in between? What's the midpoint? Like without brute forcing it in your head. How would you find it can't be 15 minus 7 divided by 2, right? 15 minus 7 divided by 2, that's 4, right? 4 is like somewhere here, right? So yeah, you add, yeah? So whoever said that was pretty close. It's add, and then it's 11, yeah? So same thing here, right? 0 plus 1 divided by 2 is a half. So this is a half, right? But that's the midpoint. And then you could do to see that this is 3 halves and 5 halves, right? So with that in mind, midpoint is you take the height at the middle, pretty much. I will sort of erase these lines to make it more clear. Whoa, that was pretty bad. Okay. And then, right, so I get 3 rectangles. And you sort of see that, like, for this one, it's hard to tell if it's over or under, right? Because on one hand, you are over right here, right here, right here, right? But you are also underestimating right here, right here, right here. Does everyone see that? So in this case, it's hard to tell whether it's over or under, right? Because it could be they just cancel each other out. Who knows, right? Or maybe there's a little over more than under, right? So for midpoint, unless you could, generally, unless you could find the exact area, it's hard to tell if it's over or under. But later on, we will be finding the exact area. I mean, by later on, I actually mean during this discussion. But so let's go over it. The width is still 1. What's the height now? The height is at 1/2, right? So I evaluate at a half. So it's a half squared, or if people like 0.5 squared. And then plus 1 times 1.5 squared plus 1 times 2.5 squared. For the purpose of this class, I trust you can all multiply and add. So it is whatever it is. So I'll just move on for now. Yeah, because at this point it's just algebra. I don't want to waste time on algebra. Okay, so now that we get the rules, I guess the next thing I guess that might be helpful for your homework is, what if it's not as nice of a division, right? How would you find it? So let's say, for example, I wanted 4 rectangles. 1, 0, 3. What would the width be? The width is not 4. Because if the width was 4, right, the first rectangle would have width 4. So this thing's already at 4, right? I want a rectangle. I want it just from 0 to 3, right? So yeah, it should be 0.34, right? And how you do it is, well, just think of it this way. I have 0 to 3. I want to cut it into 4 equal pieces, right? So how would you cut a segment into 4 equal pieces? Well, you find the length of the segment, right? And then you divide by 4, right? Fair enough, right? So if it was like, say, 1 to 5, and I want 4 pieces, well, I need to find the length of the segment. The length is 5 minus 1 divided by 4. So each one would have, the width would be 1 in this case, right? In this case, it would be 3 minus 0 divided by 4. So it's 3/4. Everyone see that? Right? I'm not going to do the right and left, but just so we all see the point, right? One way to write this is, well, the width is 3/4, so you know all the numbers already. The first term is it's 0 plus 3/4. The next one is 0 plus 3/4 plus 3/4, right? Because this one has to have width 3/4. So the next one is 0 plus 3/4 plus 3/4 plus 3/4. And then the last one is you do it 4 times, right? And you can see that when you add it 4 times, you actually get 3, right? Because 12 divided by 4 is 3. Bad drawing, should go all the way here. Yeah, and it's been the same for the previous question. It was just really easy to see, right? The width is 1, so it's 0 plus 1. This thing is 0 plus 1 plus 1. This thing is 0 plus 1 plus 1 plus 1. Yeah. I mean, I just didn't write it that way because in this example, it was pretty clear to see, right? Okay, everyone clear so far on how to get at least like the numbers here? Because I think that's pretty important, right? because those are the numbers you would use for the approximations. Okay. If everyone is good, the next step would be using n rectangles, right? So let's do right approximation. Let's do a general AB, yeah? And I want right approximation, but let's figure out the width now. I don't know, let's just say the function looks like this, who knows, right? And then let's say A is here, B is here. Maybe I'll write it bigger. Let's say actually B is like right here. Yeah, so if I wanted n rectangles, what's my width? Not 2. Again, like let me just remember, for 3 rectangles and 0 to 3, what did you do? I mean, sorry, 4 rectangles. You did 3 minus 0 divided by 4. Agree? Yeah, so here it's b minus a divided by n, right? Think of your a as that 0 and b as that 3, right? They serve the same role. So my width is divided by n. Yeah. The book just calls this delta x. Yeah. So from here we know what it is, right? Here before, what's the next? If the width is delta x, then this is a plus delta x. Next term is a plus delta x plus delta x, right? All the way to a plus n minus 1 delta x. And then the last term is b, right? B is actually just a plus n delta x, right? Because, I mean, if you can just calculate this. A plus n, what is delta x? B minus a over n. The n's cancel, a plus b minus a, it's b. Yeah, so just to convince you. So we have divided it up into n rectangles this way. Yeah. So let me erase this. So let me just ask you, what's the right approximation? What's the first term? The width is always delta x, right? Because if you look at this, how do you find the width? You take the right endpoint minus the left endpoint, right? So a plus delta x minus a is delta x. And then the width of this thing is also delta x, right? Because a plus delta x minus a plus delta x. You just get delta x, right? So the width is always delta x. And then it's the same idea, right? The right endpoint, you would take the right term, right? So for the first interval, you would take a plus delta x, right? Second interval, you would take a plus delta x, right? So this is f of a plus delta x. Another way to write delta x plus delta x is 2 delta x, right? All the way to f of a plus n minus 1 delta x. And then the last term is f of b, right? Does everyone see this? Yes, no. Okay. It's important you see this because I mean, it goes all the way to this thing, the b is a plus n delta x, right? Do you agree with that? So obviously the term before is n minus 1 times delta x, right? The thing is, it goes from a to a plus delta x, to a plus 2 delta x, a plus 3 delta x, all the way to a plus, I mean, you have n total copies, right? So it goes all the way to n minus 1 and then n, right? Except for that, for this one, we just call it b, right? I calculated it for you. So, right, because again, we want n rectangles, right? So you should have like n pieces, right? Okay. So from here, right, this is the right approximation. So we'll go back to this later. So let me just try to convince you of something. So let's go back. I know we want the same width, but let's just focus on like 2 to 3. Yeah, let's keep the area from like 1 to 0 the same. So if I just use the right approximation for 2 to 3, it would be like this, right? I would take the height at 3 and then do that, right? Now, what if I introduce instead, what if I instead introduce like 2.5? And then I did right approximation for 2 to 2.5 and 2.5 to 3. So I go from here all the way here. And then I do right approximation for 3 all the way here. Do you all see that the overestimate becomes smaller? Because if I use the 2 green ones, my overestimates are this, right? But if I use the black rectangle, like the big one, I have the red part along with the blue part. Do you all see that? Yes, no? So you sort of see that, like hopefully that convinces you, right? The smaller the width, i.e. more rectangles, the more accurate, yeah? And if that doesn't convince you, if you're like a scientist or something, right? Like, right, I don't know why I wrote the 2 there. So, right, if instead of 1 and 2, if I use lots of rectangles, let's say I use like 2 billion rectangles, right? It's hard to draw the width then, right? Because if I'm using 2 billion rectangles from 0 to 3, the width is super small, right? So how would the rectangles look to you? Like if you didn't have like a microscope, right? It would look like lines in a sense, right? Because the width is like so short, right? In a sense, right? The rectangles would sort of look like look like lines. So you can sort of see at this point you're just taking the value of the function in a way, right? You're getting closer and closer to the area because there's so little error that can happen when you like take smaller and smaller width. Is that good? Does that convince you all? Okay, so that's like a picture explanation. So here's the question then. If I want actual area, like the actual area, how many rectangles should I use? Using this fact, yeah, infinite, yeah? Now, I can't draw infinite rectangles, right? But we learned the easier way to sort of, there's a math 2A way of infinite. What is that? What did you learn in math 2A that's related to like, taking infinite stuff? Limits, good. So if I take n rectangles, to get the actual area, right? If this is the like say right approximation for n rectangles, well, to get the right approximation for infinite rectangles, well, let's take the limit. Yeah. And then this is actually this right here. So this is we define this as the area under the curve. As we take infinite rectangles. We take the limit as n goes to infinity. But we had a formula for that. This was right approximation for n rectangles, right? If I just call this the whole thing in bracket star, then the area under curve, or if you like under slash f of x, right, is given by limit n goes to infinity of star. Everyone clear so far? So now the book doesn't write it this way. They actually, I mean, it's the same thing, but they write it in terms of summations. So let me review what summation is, and then you'll see it's the exact same thing as this. Star is just that summation thing in your book. So let's review summations. So I need you all to be clear. What is sum? Let me just do it. Sum I equals 1 to 6. What does this mean? Can anyone tell me? Good. So how do you get this? Well, what it means is you plug in I equals 1, you get 1. And then you plug in I equals 2. Plus you add I equals 3, and then you go, and then this thing tells you where to stop. You do it all the way to 6, right? So like, for example, I equals 1 to 3 of I squared is you plug in I equals 1, that's 1 squared. You plus I equals 2, which is 2 squared. Plus I equals 3, which is 2, and then you stop, right, at 3, because the 3 is here. Yeah. So there's some nice formulas if I go up to n. The question would be like, what if it's up to n? And the idea is, say, we'll use this later, but there are some formulas. These are stuff you should probably just memorize. Yeah. I don't think I'll just explain the first one to you geometrically, since it's pretty simple. So, and then sum. This is actually just the first one squared. Okay. So let me just, for example, if you wanted sum I equals 1 to 6 of I, you could add all these numbers, right? You can add and you could check, you get 21. Or you can use the formula. Here, n is 6, right? So this is 6 times 6 plus 1 divided by 2. 6 times 7 divided by 2, 21. Yeah. So maybe just to convince you all, since this is just out of the blue, I'll sort of just justify this formula. Yeah. So like we said, we're summing 1 to 6, right? So we have 1, 2, 3, 4, 5, 6. And then we're summing these, right? But I'm going to sum them in a unique way. I'm going to add the 1 with the 6, 2 with the 5, 3 with the 4. Can anyone tell me what each of these sum to? What is 1 plus 6? They sum to 7, yeah? And now the question is, how many 7s do I have? Well, I had 6 terms and I paired them up, right? So I actually have 6 over 2 of them, right? And you could sort of see that's what this is. So hopefully that convinces you of the first formula. I mean, but really you should just memorize these. So with that, there's also one more thing you should know that's pretty. What is GC? What does GC mean? Group chat. I don't know. I think I'm guessing there should be like a math 2B Discord or something. I don't know. So I equals 1 to like n of a constant c. What about that? What is this? If you don't like c, let me just ask, like, what is I equals 1 to 6 of 5, for example? $30, yeah. So 5 is just a constant function, right? So if you plug in I equals 1 to 5, I mean, like, 5 doesn't depend on I, right? So you would just get 5. So if I plug in I equals 1, I get 5. Plug in I equals 2, I get 5. Plug in I equal 3, I get 5. And then I go all the way to 6, right? So how many 5s do I have? I have 6 5s, right? So same thing here. Sum I equals 1 to n of a constant is just Cn, right? Like sum I equals 1 to n of 5 is 5n. Everyone follow? So let's go back now. We could actually get the formula in the book. I claim that this is just star is just this. I equals 1 to n delta x f of a plus I delta x. Let's check it, yeah? Using the summation, using what we learned, right? This thing, right? Let's actually write out the terms. If I plug in I equals 1, right? That's what summation means, right? Plug in I equals 1. So if I plug in I equals 1, I get this. Agree? And then what does summation do? We add, and then we plug in I equals 2, right? I don't know why I did that. F of a plus 2 delta x. And lo and behold, like, it's exactly these terms. And then you plug in I equals 3, and then you go all the way to n, right? So the second to last term is f. I don't know why I keep writing the parenthesis before the f. F of a plus n minus 1 delta x. And then the last one is, f of a plus n delta x, but that's just b, yeah. Does everyone see that? Yes, no. So your book, this is exactly the definition in your book. I mean, it just looks scary because because you just need to write it out. But the book writes it like this: sum I equals 1 to n delta x f of, I think they call it xi or xi star. I forgot. Where like xi star is just the thing inside a plus I delta x. Yeah. So this is exactly the form of your book. They're just writing this thing in a nicer way. That's all it is. Okay. So last thing we're gonna do is we're gonna find the actual area. So I'm gonna go over how to do that. So let's go back to the previous. If I want the area of f of x is x squared from 0 to 3, right? The definition was what? Limit n goes to infinity, sum I equals 1 to n. So let me just write actual area. I equals 1 to n. Delta x f of a plus I delta x. Yeah. Let's fill in the holes now. What was delta x? So going back here, what is delta x? B minus a over n, right? But in this case, what is it? This is my b, this is my a. So 3 minus 0, not over infinite. No, dude. It's 3 minus 0 divided by n. Yeah. So be careful. Because when I write limit here, it's take the sum and summation. This means you sum first and then limit. Yeah, you don't just plug in n equals infinity right from the get-go, right? You have to sum first. Yeah. If it was summation and then limit, if summation was on the left, limit was on the right, then you do the limit first and then you sum. Yeah, so the order matters. In fact, the other one just doesn't make sense in this case. But yeah, so delta x is 3 over n. Yeah. Now, what is a? A is 0. So I could start plugging things in now. Delta x is 3 over n. F of 0 plus I, 3 over n. Yeah. It's nice that a is 0, so makes things much simpler. So I get I equals 1 to n, 3 over n, f of 3i over n. Now, can anyone tell me what f of 3i over n is? Good. So for those of you who, it took a long while to answer. So let me just ask an easier question. What is f of 5? Not a trick question. How do you get that, right? You just plug in 5 to x, and then you get 25, right? Same idea here. What's f of 3i over n? You just plug in 3i over n to x, right? And then, like someone said, so I get 9i squared, but the 9 and the 3 becomes 27, right? I squared over n cubed. I believe this is what you get, yeah? Okay, so 27 over n cubed is a constant in this sum, yeah? Because this sum, the variable is I, yeah? N is a variable, but it's a variable from the limit, yeah? So to make things easier, we could pull it out. 27 over n cubed. I can't pull it completely out, right? Because n is a variable here. And then sum I equals 1 to n of I squared. Now, I told you all to memorize this like 10 minutes ago, but for now we could just cheat, right? What is sum I equals 1 to I squared? It's this thing, yeah? It's n times n plus 1 times 2n plus 1 over 6. So times n plus 1, 2n plus 1 over 6. So what is this limit? So this is math 2a now. So for whoever said like whatever, like 3 over infinity, that's sort of what I mean, right? Here, yes, this is sort of like 27 over infinity, but like here we're evaluating after we sum everything, right? So I'm saying this is not equal to sum and then limit. Yeah. So be careful. Here it means limit first and then you sum. Okay. So for this, what is this now? So let me ask you all, for those who forgot math 2a, what is the, in terms of, if we think of this as a polynomial in n, in the variable n, what is the degree of the top? Degree on the bottom is, this one's pretty clear, 6n cubed, so it's 3. So they're the same degree, right? So what is if I have two polynomials of the same degree, what's the limit? Like if, for example, let's do something simple, like 5n squared plus 1, 7n squared plus, I don't know, 2n plus 6, something like that. What is this limit? Oh, sorry. This is 7. Yeah, it should be 5/7. Yeah, but for the it's the leading coefficient of the highest degree, right? Why is that? So let me just do it. Let me just remind you, Math 2A. Why is that the case? Well, let's factor out the n squared. And then let's factor out n squared. The n squareds cancel. Now, what is this equal to? Well, when n goes to infinity, where does 1/n squared go? 0, right? I mean, because denominator gets, if you have a huge denominator, you're going to get smaller and smaller. You're going to get closer to closer. So this goes to 0. Same idea here, right? This goes to 0. This goes to 0. So this goes to 5 plus 0/7 plus 0 plus 0, which is 5/7. Yeah. The idea is like when n goes to infinity, the highest power just is completely destroys any lower power, right? If you think of like the n here, when n goes to infinity is irrelevant, right? Because if you think of n squared and n, like when n is like 100, this is 100. This thing is already like 100 squared, right? Like this is I mean, this thing just completely like this thing is like irrelevant when n goes to infinity. Bottom part. Bottom part of what? You mean like this thing? This thing is just an example I came up with. If you're asking like why, I mean I just made up 2 polynomials of the same degree and asked you what's the limit. It's not related to the. I mean, yeah, it's not related to the question here. So you can see that the limit is like the leading coefficient of the highest power. Yeah. So in this case, it's easy. They're both the same degree. So what's the leading? And they're degree 3, right? So I'm asking you, what's the leading coefficient of n cubed here? Not 52. I think you multiplied 27 times 2 is not 52. But I think it's, yeah, it should be 54, right? And then the bottom's easy, right? Bottom 6 n cubed, the coefficient 6. So this is 9, yeah? And boom, that's your answer. So you see, even in the case where, say, I made it easy because a is 0, right? Obvious, but if a was not 0, right, then it would be this, right? You would square this, right? Or if you don't like the square, you would just FOIL. Agree? In which case, if you FOIL, you would get like a constant term, right? You would get a squared, which is a constant. You would get an I term, and then you would get an I squared term. Whoa, what happened there? I squared term. Does everyone agree? Like if a was not 0, right? In this case, a was 0, so everything was nice. I'm just telling you what would happen if a was not 0. So if a was not 0, does everyone agree you get sort of like 3 terms after like foiling? So the constant term and I term, you can sort of see what's happening, right? Constant term, you would use this, take the limit. The I term, you would use this, take the limit. And then I squared, you would use the one in blue, yeah? So in general, right, if you had like a degree 2 thing, like x squared, you would use up to I squared. If you had degree 3, you would use up to I cubed. And you see, that's really all we can ask for now, right? We can't really ask x to the 4th, right? We can't ask, I can't really ask you to find the actual area for now, right? Because we don't really, I'm pretty sure that there's a formula for this, but it's pretty complicated. So that's pretty much all we could get to without like antiderivatives, right? It would be it'll boil down to like solving these summations and taking limits. But yeah, so but that if you're wondering, that's why the book gives you these identities, right? It's so you could find actual areas of like x squared, x cubed, so on and so forth. Okay. Is everyone clear on this? So that's all I have for today. So unless you have questions, I will you by the way, you have quizzes, I believe, from the schedule like next Tuesday and Thursday. So don't make sure you actually come to class for next week. Other than that, I will see you all. Is it difficult? I don't make them. The professor makes them, and then she just posts it on our discussion Canvas space. So I have like no power over quizzes or midterms or finals. The professor makes it all.